That says each acre of land, each additional acre of land is worth $276,000. Okay, so that kind of makes sense because an acre is big. Nobody has an acre probably. This says something about the house size, right? So each time you increase, each square foot of home is worth $130. I would caution interpreting it that way. $130 a square foot. This includes the land cost and the age of the home factor. So it's really not $130 per square foot for these homes, but that's the value of an additional square foot when you account for the land and the age. And as I mentioned, as the house gets older by 1 year, as age increases by one, its value declines by $1,400 per year. It's not a huge number, but it is significant, right? This is significant decline. All right, any questions about this?
I'm still not sure about how to apply the R square and R square adjusted.
Yeah, so again, you've got 6 variables here, Katerina, so I can't do any better than putting them all in the equation, right? And R squared always increases when I add variables. So if I put them all in, like here in this model, I get the benchmark for what I can do with R squared. That's the best, all right? And it is a measure of the degree of fit or the amount explained by the variables, right? Now, it's a question of expediency and overfitting. Have I overfit or am I more complex than I need to be, right? So I'm going to think about removing some variables. Which ones? Ones with high p-values, okay? So we remove them.
What about the first one?
It's an intercept.
It's an intercept, so we just leave it alone.
Okay.
Okay? So when we remove the variables, the R squared drops. Yes, it will, right? What we care about is it a meaningful drop, right?
And that's the adjusted R square.
And that's how we're using the adjusted R squared.
So the fact that they were the same.
They're basically the same, right? Actually, the model with less variables has a higher adjusted R squared. So what we saw when we added variables 4, 5, and 6 is it actually went down a little bit. Not very much, but it went down. So that's an indication that maybe we picked up.
And when we apply this in this class, is that something we need to explain? Or?
Yeah, well, I think one of the things you want to do is you want to be able to say, I think these variables are useful and I think these other variables are not, right? So we have 2 mechanisms now, really. We have the R squared and sort of how good is this model overall with these variables in it, and then we have the p-values. So those are like our levers.
Okay.
The adjusted R squared is more of a diagnostic to sort of say, what are we at a sweet spot?
So if the adjusted R squared wouldn't be better, would it
Yeah, so that's a good question. So what if the adjusted R squared was lower with 3 variables than with 6? I still might pick the 3 variables. The 3 I dropped were not significant. And the R squared didn't change by very much, right? Now last class, I'm not gonna bore you with it now, but I'll show it in R. Last class I taught you a hypothesis test to actually say, are the models the same or is the one with more variables better? I think that was like the last thing I taught you guys.
Yeah.
So you can run that hypothesis test to actually check to see if the models are the same or one's better. You can do it very, very easily in R, so I'm going to show you how to do it in R.
Okay.
I hope. I'm not feeling very optimistic about R today. You might have. I'm not going to make you guys go to the lab today, by the way, but I might make you go tomorrow.
It's very cold outside.